If your LTR model wins offline but fails online, leakage may be hiding in the features. DuckDB checks expose fake gains before LightGBM learns them. This is the shape your solution will take when we finish, which checks ranking feature timestamps for leakage and reports risky signals. I'm Professor Pi, teaching search and IR with simple Python. Model builders often celebrate big offline lifts, then watch the online metric sink. Usually, it's because the model learned a signal it shouldn't have. In ranking, that often means a feature that uses future information relative to the label. You can train on it. The model looks excellent, but in production, the future doesn't exist and the model falls apart. DuckDB is a tiny, fast SQL engine that can scan pandas data frames in memory. It's perfect for quick audits, zero setup, and it speaks dates and window functions natively. Here's the plan. We'll check whether any feature was computed after the interaction it's meant to explain. Find those cases early and either fix the feature or rebuild the pipeline with history-only aggregates. The tiny example we'll use has clicks, a feature timestamp, and a label time. We'll have DuckDB compare the times, count how many rows peek forward, and then swap the unsafe feature for a causal alternative. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we stream a minimal LTR log into pandas and let DuckDB scan that data frame for timestamp mismatches. This snippet assembles a minimal LTR log by streaming the CSV payload into pandas, then immediately lets DuckDB scan the same data frame for suspect timestamps. The data frame logdf contains per query clicks, label times, and future CTR values that a LightGBM ranker would later consume. Because DuckDB can see the data frame by name, the select comparing feature time and label time runs without manual temp tables. The query returns leak count, how many rows violate causal order. And in our toy run, leaky rows equals 2, flags 2 impressions computed after their labels. Treat that leak count as either a hard stop or the trigger for a deeper audit. Next, we'll measure how far into the future those feature snapshots reach, so we can prioritize fixes. This example adds a lead_minutes column by asking DuckDB to compute date diff in minutes between each feature snapshot and the label timestamp. The query keeps rows ordered by query ID and doc ID, so later LightGBM groupings stay aligned with the original interactions. Then a second DuckDB aggregation casts the Boolean lead minutes equals 0 into a ratio, producing leak share, the fraction of impressions that peek into the future. If you widen the buffer in the where clause, that ratio drops and fewer rows remain to inspect. In our run, positive gap ratio equals 0.50 shows half of the training pairs leak. If the leak rate isn't 0, we should check how much predictive power that leaking signal actually buys the model. A quick sanity check. This code defines a NumPy-based compute NDCG helper that reuses logdf.groupBy indices to evaluate ranking quality per query. We cache the clicks array as binary labels and pass score values for whichever feature column we want to audit. Inside the loop, we use np-argsort with stable mergeAssort, so ties respect original logging order rather than reshuffling documents. The DCG and ideal DCG use the classic 2 power rel -1 gain, letting us average a true NDCG across the toy sessions. The reported leaky feature NDCG equals 1.00 confirms the future CTR signal would make a raker appear to perfectly order these pairs. When a feature is that powerful and leaking, we need a safe replacement that only uses past events. DuckDB window functions give us that history-only view without round trips. This snippet reconstructs a safe CTR directly in DuckDB by ordering clicks within each bucket partition and using a window frame that stops one row before the current event. Because the frame excludes any later clicks from the same bucket, the average uses only past data. The updated log.df now holds both the original future CTR leak and this history-bound lagged estimate for downstream LightGBM runs. A follow-up aggregation computes the mean absolute gap between the two columns, giving a quick sense of how far the leaky feature drifts from the causal one. Observing mean future gap equals 0.68 quantifies that drift and supports dropping the future-derived feature. Finally, we train a small LightGBM ranker on the clean set and compare the evaluation numbers to keep the before and after honest. This example fits LightGBM's LGBM ranker on the cleaned features, passing group sizes so the booster respects per query structure during training. The clean ranker trains on lagged CTR and safe CTR, which together use only historical evidence after the DuckDB audit. We reuse compute NDCG with the new safe CTR scores, so the before and after comparison uses the same evaluation logic as the leaky check. Adding more weak history features might slightly raise safe feature NDCG, but those attributes still can't see past label time. Seeing safe feature NDCG is 0.63 shows the realistic drop once leakage is removed. In production, make this audit a pre-flight in your feature pipeline. Run it nightly or before training. If it finds issues, fail the job and attach the flagged rows for developers to inspect. Quick recap. This is a DuckDB-based audit that compares feature timestamps to label times in ranking logs. Use it whenever offline gains look too good to be true, or when features come from event streams. One caveat, it catches timestamp-based leaks, but it doesn't replace careful review of complex joins in your pipeline. Next step, scale this audit to a larger corpus and measure how leak share changes with a rolling time buffer. Then, use the results to set a production guardrail threshold. If short practical IR helps, subscribe and watch the IR videos.